Yeah. Today we will discuss about Hive. Yesterday we had a small impromptu session, but kind of it didn't go anywhere. So I thought, okay, let me just do it properly. Okay. Yeah. So we are basically um, discussing about Hive. What is Hive architecture and why do we need it in the first place, right? So if you remember in our previous sessions, we discussed about a couple of things on storage, on processing, very huge amounts of data, right? Like terabytes of data, let's assume raw data, right? We kind of established a pattern where we wanted to store data redundantly in a distributed system that can scale on our demand, right? On the demand that we have, be it on the side of compute or be it on the side of just pure storage, right? That solution was hdfs, right? It's a block storage where we store data, right, in blocks across machines and multiple copies of the same block. Now when we wanted to process it, we had a new paradigm called map reduce, where even we had distributed data across systems, we could use the metadata that is stored in one name node in HDFS to identify what are all the blocks present and the locations of them on each server, on each data node, and then we processed it using the logic that we have created. And we have done that in MapReduce, right? We have done that in MapReduce. One of the examples that we see here is a word count, right? We have written this in pure Java code, and we have done our created our own application in MapReduce so that it will process the data in our HDFS location, the raw text files, and count the words of it, right? So now we have to think about this in a very proper manner, right? Because whatever you are seeing here, right, whatever you are seeing here, starting from this to until here, all of this is boilerplate code, right? Boilerplate code in MapReduce, right? This is all boilerplate code. And not only this, we have to like not just repeat, but we have to do the similar levels of boilerplate code across all of these, map, reduce. Again, this is also boilerplate, right? All of this plate. And this is also boilerplate code, right? This is again a reducer, right? This is a reducer here. The problem is not just the boilerplate code. The problem is the map and reduce code here. It is very primitive. It is very primitive in nature. Let's suppose I have, three different tasks, right? A, I want to read data from a location in HDFS, right? Read data from HDFS, right? Second one, this is first. Second one, I want to filter them. I want to filter them. Filter. Third one, I want to group by, right? Group by. Now, reading and filtering will be one map job. It is map only job, right? Map only job, right? If you have to convert these operations into map reduce paradigm, right? This is map only job. Both of them are map only job. The group by will again be separate map plus reduce job. One map plus one reduce job, right? Because we'll have to provide the filter data to the group by operation. Within that group by operation, it has to shuffle all of the data per key to the respective nodes in our cluster, in the Hadoop cluster. And then we'll have to reduce, we'll have to count or perform an aggregation like sum or count or average, all of these operations as reduce operation later, right? Just, these three operations will give us like two map operations. At least, this is at least two map operations and one reduce operation, right? And we have to write boilerplate code for all of this, and we have to write boilerplate code for all of these operations. And especially we have to tie them together. We have to tie them together. All right. If you are working in a large, with large data, with sophisticated analysis tied to it, right? This is feasible, but you have to abstract it, or you have to create abstractions on top of these operations all the time, right? Because, right, one single Gubrai operation is taking one map and one reduce, right? Okay, I'll create one abstraction out of it, right? Okay, filter, again it is a map operation, right? I'll create another abstraction on top of it. What table, which location, I will pass it here, right? Location, hrefs location, I'll pass it and it will give me filter output, right? This is filtered output. Filtered output, right? This is filtered out. Now, again, this filtered output, I have to pump it to our group by operation, right? Again, I'll create a abstraction over it. Okay, I'll create an abstraction over it, right? If I'm a programmer, I'm going to do this, right? So, this is very boilerplate heavy code, right? That is the first concern. Second thing is, it is only programmer friendly. It is only programmer friendly who are deep into Java ecosystem, as well as who are deep into programming, right? Who are deep into programming all the time, right? Forget about chat GPT and all of that. None of that existed earlier, right? None of that existed earlier. So this means that we are seeing one, lot of boilerplate code, right? Boilerplate code. And second, we are seeing, we have to build lot of, you know, um, abstractions, right? Abstractions, abstractions on top of, MapReduce, right? On top of MapReduce to perform any simple operation, right? So this is very important for us to understand, because even though MapReduce is super duper capable and it can scale out a lot, right? It But the ergonomics of it is very bad, right? Ergonomics basically means how a developer can understand it and how fast they can get the work done, right? This is all very cumbersome, right? So that's one thing. Third, the main reason, right, it is very technical, you know technical, tool, right? Very technical tool. Like, you have to be very much into Java, all of that, right? All of the ecosystem and all of that, right? So because of this, right, the whole data lake, data warehouse thing kind of feeling very on the shaky grounds, right? We couldn't get a simple enough tool to query the data. Why do we want simple enough tool in the first place? Because, like, let's be very honest with you, right? I'll be very honest with you. My business folks, right? Business in any company, right? In any company, business folks, right? They don't, right? They don't care whether you are writing MapReduce code, whether you are writing SQL code, whether you are writing code for the world's fastest database or not. What they care about is consistent data, faster access to data, and anything that they can look into the data by themselves, right? They don't want all of these complexity for them, right? And moreover, all of the data folks at that point, right, when Hive first started, right, These are from business backgrounds or they are from, IT backgrounds, right? Now, the idea, they had for, any type of, data side of operations, right, is with SQL a lot, right? Is with SQL a lot. If you want to create a report, yes, I'll do it with SQL. If you want to create, business process, yes, SQL, is the standard for them, right? So they didn't feel very excited about all things, MapReduce like this. You know, they didn't feel anything, exciting about this because it's too complex. A second, you have to write a lot of, boilerplate code and only programmers can understand. And these people, data folks, whoever were working with earlier, data warehouses that used SQL, they were kind of feeling like, not great about this development, right? And maintaining Hadoop clusters was one challenge, right, on one end. And creating very complex systems that can handle business is one huge, missed opportunity, in the sense that you have to deal with a lot of complexity to just get simple results out of it, right? So then came Facebook and said, okay, guys, let's be real with our work. What we will do is basically we will create an abstraction on top of your MapReduce so that we have a simple enough system where we have SQL like query interface to perform all the operations that we do, right? Why do we want like SQL interface, and why are we fixating on SQL interface in the first place, right? All of the business data, right? All of the business data, right? Business critical data, right? Critical data. All of the business critical data existed in RDBMSs, right? RDBMSs. And now, not only that, right? It is also in tabular format. It is also in tabular format, right? Most of the time, not all the time, but most of the time, right? In a tabular format. That means we have rows, columns, and column metadata, right? The data is arranged in such fashion. Now, what is the best language to deal with this kind of data? That is SQL. And that is SQL. Now that we know what we want, right, out of HDFS, and we have a paradigm that we already described, that is MapReduce. So we are missing one critical piece, right? That is SQL, right? So Hive created Hive, like, conceived the idea of Hive, right? Was conceived at Facebook to create a data warehousing solutions. Data warehousing solutions were already present, right? Were already present in the market, basically from Oracle, right? Oracle data warehouses and IBM DB2, right? These are your relational data warehouses, right? Relational data warehouse. That means only tabular data for the most part, right? They didn't, and there, at that time they didn't have anything like a data lake and all of these newer forms of paradigms built into these data warehouses. And for example, these also costed a lot of money and in terms of license and maintenance as well. So Facebook didn't want to pay them for obvious reasons, because their data was really huge and they were one of the most popular sites on the internet. So they are creating a lot of data day in and day out, right? The second thing is that they were heavily invested, like other internet scale companies. They were highly in like invested in HDFS plus MapReduce, right? The whole Hadoop ecosystem as well, right? All of this is Hadoop ecosystem, right? They were like, they were heavily invested in Hadoop ecosystem, right? Now, since Hadoop, all of this created a lot of flexibility for them. What they did was, they created a warehousing solution on top of it, called it Hive. Called it Hive. What is a data warehouse here? Data warehouse here in this particular scenario means that you have a data lake, right? You have a data lake, that stores, files, right? That stores data in files, and you have processing engine, basically your, MapReduce, right? Now you want to create, right? You want to create an interface where you can query this, you can query the files, you can query the data in these files, using a simple language. That's what their primitive definition is. Very a simplistic, definition, right? That's what they wanted to do, right? For that, MapReduce, even though it is very scalable, it was primitive, and your all of your data, business critical data, is in some kind of tabular format or relational format, right? Next up is that they have decided to go with this, right? Before we dive into this, let's just put some like background information on what is a data storage system, right? Like rdbms. What is an rdbms? Let's do this, right? An rdbms is a storage engine first, right? A storage engine, that's where your data is stored, right? That's where your data is stored in a very proprietary format, right? In a very proprietary format, right? This is where data is stored, right? In in a db specific manner, db specific manner, right? db specific format, right? For example, if you had had a chance to, if anyone had a chance to look into like older database formats, right? Their storage engine is very specific to them, like very very specific them to them. Like MySQL, right? MySQL will have their own SQL, storage engine, where they will store the data in a very certain format that is very different from, let's say, SQL Server from Microsoft, right? SQL Server or Oracle, right? Oracle, or even Postgres, right? Postgres. These are very popular, data, bases, right? They have very tightly coupled, data storage engines that stores the data in one thing, right? And they also had a query engine, right? Query engine, where you fire up, a SQL query here, and this query engine will take that query, right? The raw text of the query, convert into a plan, and then execute your query on top of your storage engine and get the results back. And you, as a user, will be getting the data, through that SQL query, right? This is what it is. Query engine, if you dive deep into it, there are a lot of components in it, but we will just skip for this discussion, right? So now, if you scale that idea to something like Hadoop, right? Hadoop system, this Hadoop cluster, right? Or this HDFS is your storage engine, right? Is your storage engine, right? Storage engine. Now, MapReduce, this is, we consider this as a our query engine slash programming paradigm, right? Query engine slash programming, you know, right? Query engine, right? Basically, what MapReduce does here is that it will talk to your Hadoop cluster to get the data, right? To get the data within these nodes itself, within these nodes, and execute them, parallelly on these nodes, right? Okay. Since MapReduce is very primitive, what Hive people did is basically they created a interface, an abstraction on top of MapReduce, that gives us a SQL interface, SQL like interface to query this, data, right? This is the, simplified architecture of Hive. Basically, Hive has one metastore, we will discuss about it. The second is an execution engine. The third is the user interface, be it, command line, be it, user interface like web interface, right? Interface, or something like a JDBC or ODBC, or even thrift server, right? These are all your, interfaces, right? Hive interfaces. Hive supports multiple interfaces basically because your, database, right? Every single database has CLI, normal, like MySQL, Postgres, all of them. They have a web interface or an application interface like MySQL, like something like this, right? This interface, right? Hive supports this kind of interface. And finally, JDBC and ODBC. JDBC is Java Database Connectivity, or ODBC means Open Data Database Connectivity Library, right? Where JDBC is developed by Oracle, ODBC is strongly supported by Microsoft, right? These are open standards and one is proprietary standard, right? Thrift is developed by, again, Facebook for various purposes, not just, Hive, right? So this is high level architecture. Let's now dive deep into this architecture, right? Before that, we will discuss about, Hive components, basically. Hive components, right? Hive components are pretty interesting, right? Let let's take first one, that is tables, right? What Hive says is basically that everything you deal with within a database, right? You deal with in the terms of table objects, right? Table objects. Let's say in MySQL, if you want to, like, deal with any data, all the data is stored and abstracted away to a normal user on many, levels, right? Your storage engine, your query engine, all of them, combined and tightly coupled. Here if you check, all of this is one system, right? These are all components and this is one database system, and all of these are tightly coupled, right? Tightly coupled basically means your MySQL engine has its own storage engine that is, that only works with, or that only is tied to the MySQL query engine, right? This is what it means tightly coupled, right? Here, that is not the case. With Hive, it is not the case, right? So a lot of components are shared between data warehouse and data database. So that's why, things are pretty much, looks similar, right? So what Hive did here with, let's forget about Hive for a second, right? If you think about this only this map reduce, Hadoop, HDFS and, map reduce, right? If you think about only this part, right? Only this part, only this part, right? What do you see? You see that, you know everything that you are doing is an operation on a file, operation on a file, right? What do I mean by that? Operation on a file. This is pretty interesting, right? Okay. When we had data on a Hadoop cluster, right? How did you access the data? How did you access the data? Right? We had HDFS commands, right? We had HDFS commands. What are HDFS commands here? Your POSIX like, commands. What are POSIX commands? POSIX like commands, right? Right. POSIX like command. What are POSIX like command? HDFS commands, right? Let me just give you an example. If you wanted to, just list the files, right, in a certain location, right? Basically, these POSIX like commands are, your Linux style commands, right? In Linux, you have, ls to list all the files, right? Copy to copy all the files, right? rm to remove all the files, mv to move all the files from one location to another, and basically you had, cat, right? Basically to just get the contents of the files, right? And all of these are your typical, Linux commands, right? If you wanted to get data from directly from the Hadoop cluster, right, we had to, like, prefix it to HDFS, DFS, and, all of this, right? LS and CP likewise, right? RM likewise. And if you wanted to put any data in Hadoop cluster, it is hrefs dfs again put, right? Or if you want to get any data from Hadoop cluster, right, directly. These are all like direct file operations, right? These are all direct file operations. You are directly, getting the data directly from the files, right? Directly from the files. That was not the case, right? Your storage engine here had files in its own format. This storage engine stored your data in files, right? But you as a user never, like saw physically about how these files are stored in what format, and get the data directly from the files, right? It was not allowed at all, right? You had to fire up a query to a query engine. That query engine in turn would have given an optimized plan for the storage engine to retrieve the data, and that data we used to again get back to the query engine, which is displayed to us in a neat little web interface or your application interface in tables, and in tables, right? So this is what it is. Actually, your storage engine does not s- store the data directly in the form of rows and columns. It stores in a very optimized format. But none of that exists in here, right? All of these are file operations directly on file, right? On file. How we do in Linux, right? In Linux or Unix, right? Like Linux. This is all like Linux, right? Now, when MapReduce came, it worked with these APIs from, to get the data from the Hadoop cluster, and said, okay, boss, I want to get from a location, right? When the MapReduce is running, I want to get the data from a location. Let's say user slash warehouse, right? This is my location. This is my location, right? The name node knows what are all the blocks that are present for this location, in this location, right? Let's say sales, right? Sales. This is my final location. The name node knows where these blocks are. It will give this particular MapReduce program of the block locations, right? Block locations, right? And this MapReduce reads the data, this MapReduce that runs on each cluster, right? The task, right? T1, T2, T3, and T4. These tasks will access these blocks, right? These tasks will access these blocks in these particular locations, and then they will do the operations, right? This is how primitive it was. Now, if you compare that to any database, right? Any database like MySQL, you are seeing, right? All I am doing here is, let's say I'll just query this data, right? Let's say I'll query this data, right? I'll use some commands here, like use Chinook database. This is one database that you are seeing on the right. This is MySQL Workbench, by the way. This is an desktop application that connects to your MySQL database service that is running in my laptop, right? So Chinook, I'll give this and select star from, right? Select star from your what is it? Artist, artist, right? Now, if I run this, right, I am getting the data in a tabular format. But if you check here, all of these, right, these file operations, right, these are very different. These are very different to what we are seeing here, right? This is how normally databases would have worked. But in here, when we had only MapReduce, right, the MapReduce API internally did all of these operations, right, based on what we had, given that what we had, uh, provided with the MapReduce had its own APIs to read the data directly from the files, right? Now, this was how it was, right? And you could always check the data directly using hdfs commands, right? Without do this is very dangerous, right? This is very dangerous whether you have permissions to that data or not. This is very dangerous, right? Because your MapReduce can like access the data through its own interface, right? Through its own APIs. But if somebody, like modified the data, mid run, or like did some operations on the files, there is no stopping it, right? There is no stopping anyone here, right? I, as you know, a user of this, MapReduce cluster, can send one request, you know, directly to the Hadoop cluster to put some data or to delete some data, right? And my colleague, in could schedule a job, a MapReduce job to run, on it in the same location, on the same location here, right? Here he is trying to read the data. Here he is trying to read the data. Here I am, like adding the data and deleting the data, right? On a different level, on a different level. One at file level directly on the storage on the Hadoop cluster. One through like data that processing done through MapReduce framework. It kind of creates some sort of confusion and all of that. In a largest company like Facebook, it's a absolute hell, right? It's an absolute hell because if somebody is directly dumping the data into a location and the other person is trying to like read the data through MapReduce, right? It kind of creates a very inconsistent data, right? So this is not what we want, right? This is not what we want at all, at all, right? We wanted to have one single consistent user interface, right? That is where Hive comes into picture. Hive comes into picture. What Hive does is, right, let's forget about MapReduce, like Hadoop file commands and all of that. We will create table like entities. We will create table like entities, right? What are these table like entities? Table like entities has a permission to access data, right? Data from a location, from a location, right? From a location, right? And with some metadata, right? With some metadata, right? It has a location, it has a metadata, and it has file format, file format, with it, right? These three components. Majorly these three components, we can have lot of metadata present for any table. What this Hive component, table component says that is, I will act like a DB table, right? Not exactly a database table. I will act like a database table, right? Database table, right? Because I have, schema here. Metadata basically means schema, right? Schema means your column information, right? Your column information, right? Column information, right? Column info. I have this. I have what file format it is stored, and I have where I know where it is stored. Right. I'll act like a database table. I'll act like a database table. You can have permissions on it, and who can. Okay, sorry. And who can access this data, right? And you can set. You can treat me like a database table, right? You can have permissions on it, and you can treat like a database table. What really happens here is that we are abstracting our data that is stored on HDFS to one more level, right? To one more standardized level where I can say that for any like whenever you want to access a location on HDFS for a particular data, I can say that okay, this location, right? This location means like sales data. This location means marketing data. This location means like engineering data, right? So now when that specific location means something, we can abstract out to saying that okay, I'll make it a simple enough way to create that. What happens when we once we create tables, right? Once we create tables, Hive provides something called as Hive QL, which is like SQL for Hive, which is like SQL for Hive, where using the metadata that we received, right? The schema of that files that has, that holds the data, right? We can write SQL queries. Again, what is SQL? SQL is so yeah. Again, what is SQL? SQL is basically your language to, it's a declarative language to provide a way to get the data, right? We will say select, right? Select star from table, right? What this table, you know is basically your location of where the data is present on the disk, right? Your metadata, basically your schema, right? Your schema, your column info, all of that, right? Your schema, and what format of data it is, right? Why are we mentioning format here? Because we understood, right? In our data lake, we can have multiple types of data, right? We can have multiple types of data, right? JSON format, text format, CSV files, Parquet format, and different formats, right? Our like our idea is that it doesn't matter what format we are receiving in. We want to store the data as is for once in raw format, and we can abstract the data from the raw format using like simple queries, right? Earlier it was MapReduce, now it is simple queries like this, and we want to store the data in a much more optimized formats later on, like maybe in Parquet, right? That's what it is. So now when HiveQL was created, right? They said that it works on top of your Hadoop, right? It has different way of enforcing the schema, that is read on schema on read enforcement, and it supports much more better optimizations than just running queries on a file, right? It supports something called as partitioning and bucketing, and it can also provide support for complex data types like map database, maps and structs, right? So this is what the promise was. And again, all of these table, whatever metadata that it has, it will be stored in a central catalog format in a catalog called Hive Metastore. Hive Metastore, right? Hive Metastore has your typical SQL like databases, you know, and tables, databases and tables, right? One database can have multiple tables. That's what this means, right? Okay. Any doubts till now? Any doubts till now? Cool. Once we understand, okay, what we are doing here, let's just dive into what Hive architecture looks like. What Hive architecture looks like, right? Hive is basically, understand this as a query interface, right? Query interface that abstracts away your MapReduce code, to a point where you are not writing MapReduce code at all. You're not writing MapReduce code at all. Okay. All of this, right? All of this is not written by you. Hive itself will convert your SQL queries or HiveQL queries into what we call as MapReduce jobs, right? That's what this is, right? So we have discussed this, right? We have discussed this in a very simpler manner. This is your user interface, right? User interface, right? What do I mean by that, right? Suppose I have a querying application like your um, you know like what is it, dbeaver, right? Dbeaver, or JetBrains one, right? Data grip, right? Data grip, or Hives, web UI, right? All of these will connect to your Hive through a JDBC connection or a ODBC connection or a Thrift connection, right? So this is what this basically means. Hive client means, right? You will be querying this data from these interfaces using any of these, connections, right? These connections will connect to Hive server, right? Hive server. Why it is mentioned as Hive server 2 here basically means, this is Hive v2, right? Hive version v2, right? Hive had significant changes over the time. The one of the prominent one was from Hive version 1 to version 2. That's why we have Hive version 2. Right. Beeline is a CLI, right? Beeline is a CLI, and Hive itself has Metastore where it will, like has all the catalog of all tables, right? In what database, what table is, and what that table is pointing to which location in your Hive. Sorry, in your HDFS, right? That is present. Again, Hive will have driver where it will take the request from any of your applications through these connections, and it will say, okay, this is where your Hive code will be provided to your MapReduce job, right? Your driver is where the application is being run, right? This is the primary interface for your Hive as an application, right? Where once you fire up a query from your Hive CLI or from any of these like applications, right? It reaches Hive server through these connections or directly through Beeline, right? Once it receives it, right, it converts this raw SQL query into, right, compiles it into a plan in the compiler. It will, the compiler will basically check whether the syntax is right, whether it logically makes sense, whether that table is present or not. It will, this compiler will go to your Metastore and check whether here this table is present, whether the SQL query is correct or not, and finally it optimizes it. Right? Once it is optimized, it will be again sent to your driver, and your driver will create the MapReduce version of the code. Right? It will transpile the code. Transpile means converting the data converting the code from one language or one language to another language. Here it is simple SQL query. It will be converted to MapReduce, which is in Java, right? It will convert SQL declarative statements into MapReduce APIs, into MapReduce API code, right? And then your MapReduce API code will run on your HDFS, right? This is how it will look, right? This is how your architecture is. What is a metastore here? Metastore is a database, right? Database. Metastore is a database, right? Popularly, it is MySQL database, right? Popularly, it is a MySQL database. Why it is a MySQL database, right? We understood that it holds catalog information like your table location, right? HDFS location, right? Location, right? Right, every table, Hive table will have one you know HDFS location, two file format, right? File format, and three column schema, column schema, right? Column schema. Now this will be stored for each single table in your catalog, in your Hive Metastore. Now we already have HDFS, right, as a storage engine, as a storage engine. Why do we need a database here? Why do we need a database here? Again, because A, our column schema can change anytime, right? Our column schema can change anytime because we are storing the data in a data lake. This is a data lake, right? There is no schema, fixed schema concept here in data lake at all, right? That's what data lake means, basically, right? You want to have the column schema changed very quickly, right? If you think about it, the column schema can be stored in one single row, right? It can be stored in one single row. Row based operations or simple one record operations are not great, you know uh, on your HDFS. HDFS stores bulk data, right? HDFS stores bulk data, like too heavy of data, and If you want to do any operations on it, you are performing, batch operations, or, very huge operations on all of these bulk data at once, right? That is what HDFS is for, right? It is not the engine to perform, like, single, column or row updates, right? That is not the case. For that, database is always the king, right? Second option, second thing, one, you know why do we need MySQL? One, you know um, transactions, transactions, right? We need it for transactions and um, row level operations, row level operations, right? Why we want transactions here? Why we want transactions here? We want transactions because any changes to our column schema, or any changes to any of the things in our, metadata, right? It has to, happen in a transaction, right? If something, goes down in your Hive server, if something goes down in a Hive server, we want to have a last, known state of our Hive, catalog, right, of our Hive metastore. That's why we need transactions. And again, row level operations, yes, because our, column schema, or all of the column data can be stored in one single one. Databases do row level operations very well with transactions, yes, that's why we chose that. Second, this data lake is a certain, a type of system where you cannot do, like, updates. You cannot do updates here, right? All you do is just store the bulk data, read the data in batches, right? Updates for rows, right? Updates for rows, like one or two rows. That's not what HDFS is for, right? HDFS is only for to just dump the data, right? It follows this worm convention, right? Write once and read many times. That's what this is for. If you want to update any data, you have to rewrite the whole table. You have to rewrite the whole table, right? That is a very costly operation, right? Considering this only HDFS is only for OLAP kind of things, and you have to rewrite the data all the time, right? This is not good to have, simple column, changes. Let's say you want to change a date column to timestamp column, right? Timestamp column, right? You will have to rewrite the entire catalog. You'll have to rewrite the entire catalog for this just simple one column in a one table, conversion. You have to rewrite the whole thing. You have to rewrite the whole catalog again and again, because all of the catalog will be stored in one table, right? So you'll have to rewrite the whole thing once again if it were to be stored in a data lake. So that's why we avoid that. So it is stored, the column, all of the column metadata, everything is stored in one single database, right? That is completely different from the data storage that we see in our, HDFS. So that even if something goes wrong here, it doesn't affect the storage here or any operations. It will only, affect the Hive and above applications that are built on top of Hive. Okay. Now, finally, I wanted to, like, show this one, right? This is your UI, basically your, querying interface, querying UI, right? Where you execute a query and it reaches to the driver first, right? And driver will send it to compiler. This is your second step, where compiler, understands what query you have written, whether it is syntactically correct, whether it is logically correct, and whether this query can be, executed on top of your data. Yes, okay. Because this query, has access to your metastore, it can get the metadata. It can get the metadata. Like, metadata basically here means your table information. Right? Table information, again, we have seen this, right? Table information includes your HDFS location, your file format, and your column schema. All of that, right? If we know that, okay, let's just say select star from sales. I have, right? sales. I have done this, right? I have done this. Now, when we executed this query here, right, it reaches driver, it reaches compiler, and it has to check whether this syntax is correct. Of course, it is correct. But if the sales table itself is not present in your metastore, right, it will not execute because there is no object like that, right? So to know whether the sales table actually exists or not, it will send a metadata request to metastore once. Since it is a database, it will quickly give us the result, right? And then it will check again, right? It will check again. Once it checks the logic of this particular SQL query that we have sent. Okay, it will send a plan. It will not send the query back. It will send a plan to how to get the data, where to get the data, and how do we get it in a much more optimized one, right? It will send all of that one. Once it does that, right? Once it does that, right? The right the driver also sends the data. This is Hive driver basically, right? This is again Hive driver, not your HDFS one, not the name node, right? This is a separate one, right? What it does is basically it will send a request to your execution engine. This is where your queries will be executed in MapReduce code, right? Right. So execution engine basically says that, okay, now since we have our query plan that we got from our compiler, I will send it to execution engine, right? Execution engine again uh, takes that plan and creates a DAG basically, right? DAG here basically means directed acyclic graph. What it does is your SQL query will be converted into number of MapReduce jobs. One SQL query, right? One SQL query will be converted into n, MapReduce jobs. N MapReduce jobs, right? N MapReduce jobs, right? N MapReduce jobs here. These MapReduce jobs will be arranged in phases. These MapReduce jobs will be arranged in phases so that we know, like, if it is a single table, it will be single way. If it is multiple tables, we know, like, this is T1 and this is T2. This single SQL query, right? It will be converted into multiple MapReduce job that is arranged in such a fashion that it will start with tables, it will read data from tables, and it will create a plan such that it will arrive at the final conclusion. It will arrive at the final conclusion. All of these planning and arrangement of tasks map under reduce tasks, right? These are all individual map and reduce tasks, by the way, right? All of these will be done by your plan where you are planning to convert from SQL query to multiple MapReduce job. That will be sent to your execution engine, and once you have executed that, you get the results into your driver, and that driver will again send the results to your query interface where you will get the tabular data, right? Metastore is the important, Metastore and execution engine are two important components here. Driver is basically like coordinating all of these tasks, right? This is how your Hive engine works, right? So even while executing, your map and your reduce jobs will have metadata information getting from your metastore, right? So this is how it is. This is Hive, this is Hadoop, your HDFS cluster, right? This is what it does. This is architecture level, way. In the next session, we will discuss about how do we create tables, how do we run queries, how do we get results, all of that. Okay, cool. Any doubts here? Anything? Okay, cool guys. I'll stop sharing my screen and recording.